Hello everyone, my name is Bhumi Salam. I am a graduate student working under Dr. Paudel at South Dakota School of Mines and Technology. Today I am going to talk about ab initio study of alloying of MnBi to enhance the energy product. For this work, we have collaborated with South Dakota State University, and this work is funded by South Dakota NASA SCORE. Permanent magnets are very essential for the modern technologies like generators in wind turbines, motors and generators in electric and hybrid vehicles and flying robots, etc. At present, the most promising permanent magnets are rare earth-based dysprosium added neodymium magnets, which have very high performance, but they are very expensive and rare, so that we need to find a magnet that has high performance as well as have low cost. And one of the candidate is MnBi, because MnBi is rare earth free. It has large coercivity and magnetocrystalline anisotropy. It also has high Curie temperature and positive temperature coefficient for both coercivity and magnetocrystalline anisotropy. So it is also useful for the high temperature application. But it has a drawbacks that the MnBi magnets has relatively low saturation magnetization. So in this work, we try to alloy MnBi with other foreign elements to increase its magnetization. This is the top view of the MnBi crystal structure, and it shows that MnBi crystallizes in hexagonal nickel arsenide type structure. And this is the side view, which shows that there are plenty of empty spaces in MnBi where we can add the foreign elements. If we add the foreign elements at one of these empty sites, we call it half-filled case, and when the element is added to the both of the empty sites, we call it full-filled case. First, we calculate the formation energy of the alloy to find the stable alloy. And the alloy having the formation energy negative are thermodynamically stable. Our site occupation calculation shows that if the formation energy is greater than 0.2 electron volt, the interstitial site occupancy is smaller than 1% at 500 Kelvin, which means that the number of foreign elements added to MnBi is very, very small. And this small number of added elements could not change the magnetization to a significant value, so that we are interested on the alloy whose formation energy is less than or equal to 0.2 electron volt, where the site occupancy is greater than 1%. We alloy MnBi with all possible elements present in the periodic table and calculated their formation energy. Here, the letter in each box represents the element added to MnBi, and the values at the top represents the formation energy when it is half filled, and the values at the bottom represents the formation energy when it is completely filled. From our table, we highlighted the alloy whose formation energy is less than or equal to 0.2 electron volt. And from our calculation, we found that MnBi alloyed with these elements, lithium, oxygen, fluorine, scandium, rhodium, palladium, and platinum, have the formation energy less than 0.2 electron volt. So these alloys are the alloys of our interest. Now we want to calculate their magnetization, and for bulk MnBi, magnetization is equal to 3.54 Bohr magneton per manganese atom, and taking this as a reference value, we calculate the percentage change in magnetization in these alloys. And we found that MnBi alloyed with fluorine, scandium, and yttrium decreases the net magnetization. And to explain this, we also calculate the density of a state plot. Here in figure C, we can see that fluorine P states hybridizes strongly with bismuth P states, and these induces a small magnetic moment on themselves. And these small magnetic moment on fluorine and bismuth uh, couples antiferromagnetically with the magnetic moment of manganese, thus decreasing the overall magnetization. Similarly, in case of scandium and yttrium, their D states hybridizes strongly with the minority D states of manganese, and they induce a small magnetic moment on themselves, which couple antiferromagnetically with the moment of manganese, thus decreasing the overall magnetization. When MnBi is alloyed with lithium, oxygen, rhodium, palladium, and platinum, we found that their magnetization increases after alloying, and it increases by up to 14%. And to explain this, we also calculated their density of states. And from the figure, we can see that rhodium, palladium, and platinum D states hybridizes strongly with the manganese majority D channels, which induce magnetic moment on themselves and enhances the magnetic moment of manganese also. And their magnetic moment have been coupled ferromagnetically with the magnetic moment of manganese, thus increasing the overall magnetization. Similarly, lithium S state and oxygen P states also hybridizes with manganese D states, and they couple ferromagnetically with the manganese moment, increasing the overall magnetization of the alloy. Now, we find that the magnetization is increased in these alloys. Now we want to calculate the coercivity and the energy product. To calculate the coercivity, to find the coercivity, we calculate the magnetic anisotropy energy. And we found that magnetic anisotropy energy increases in these alloys and increases by up to 20.27 in case of half-filled palladium. Now, we want to calculate the maximum energy product. And for maximum energy product, the hysteresis curve should be almost rectangular. And taking this hypothesis under approximation under consideration, we calculate the maximum energy product of these alloys. And we found that the maximum energy product increases as a result of alloying. And the energy product increases by up to 32% in case of rhodium. Now, we found the alloy that are stable, that have the increase in magnetization, their coercivity increases, and their energy product also increases. Now we want to look at their Curie temperature. For that, we calculate the Curie temperature in the Millfield approximation using this equation, where delta E is the energy difference between the ferromagnetic and the interferromagnetic states. And the Curie temperature calculation shows that due to alloying, Curie temperature decreases, but it is higher than the room temperature. Also, we found that the volume of the alloy increases after alloying. In summary, we found that MnBi exposed to lithium, rhodium, palladium, platinum, and oxygen results in increase in magnetization, increase in coercivity, and increase in energy product. We think that this study will help to down select the element for doping of MnBi for further detailed theoretical and experimental study. This result shows that MnBi could be developed to be a low-cost, high-performance magnet. Thank you for your attention.